And the prices, for example, when we talk about stablecoin protocols, we are basically dealing with prices, and they are real values in nature. So it makes sense to use this library. Another choice that we needed to make was how to represent state. So what do I mean by state? In any stablecoin protocol or any software implementation, you have this notion of state, which represents the state of the real world at any point in time. So for our purposes, it's the state of the stablecoin protocol at any point in time, and it's composed of some variables which vary with time. For example, the number of neutrons that you have in circulation, which is basically stablecoins. The number of protons that you have in circulation, which are the reserve coins, and the number of base coins, which are locked in the contract, and P0 star, which is the target price of one stable coin in terms of base coins. So this is the price that we are tracking basically, and we want our stable coin to be as close as possible to this price. And this varies with time because the price of base coins fluctuates, and we need an oracle for this to get this price. But all these four things, they vary with time, and they are variables. And we have some constants as well. For example, Q star, fission fee, fusion fee, beta decay fees, and time period. So they are related to some details of the protocol, which is not relevant, but the only thing to know is that they are constant, and once defined, they cannot be changed. So when we're proving theorems, we also need a way to keep track of past reactions to calculate the beta decay fees. So one of the functions for this protocol is beta decay, and to calculate the beta decay fees, you need to keep track of the reactions that happened in the past. So we need some sort of notion of history, and how we do that is by using something called a trace, which is just basically a list which keeps track of the reactions that happen on the stablecoin protocol. So this is a visual representation of the state. Like you have this big state, and it's composed of the stablecoin state and the trace. The trace basically is a history record for all the reactions that happen. And the stablecoin state is further broken down into the reactor state and the exchange rate. The exchange rate is the P0 star that I mentioned earlier, which is the target price for our stablecoin. And the reactor state is composed of base coins, stablecoins, and reserve coins. And this is exactly how we represented it in code, in the formalization, and it's a very modular structure to ease formalization. So to represent these entities, we make use of something called records in rock, which is these are some images of how we represented the state. So over here, like I've defined all the variables and the constants. This is how I'm making use of records. So to understand records, you can just think of them like objects and object-oriented programming. This is how I represented the reactor state, the stablecoin state, and this is how I represented the trace, which, as you can see, it's just a list of reactions that happened in the past. So it's a list of tuples, and every tuple consists of like a stablecoin state, a timestamp, and the reaction. And the reaction is defined above, which could be like a fission reaction, fusion reaction, or the beta decay reaction. So now, concluding the talk, I will talk about some of the bugs that we detected through this formalization, which is the main, which is why we started this formalization in the first case. So one of the bugs that we found was in the on-paper proof, we were making an incorrect assumption that the price of volatile tokens, or also known as reserve coins, is unchanged after the fission reaction. This was obviously an incorrect assumption to make, and we had to fix the on-paper proof for it and then formalize it again. There was another bug, which was when we were calculating. So in Theorem 1 for this protocol, we were basically trying to come up with an expression for how many base coins we need to get one stable coin. And first of all, we were trying to find an exact expression, but this expression was sort of recursive because it depended on the base coins burned, what we were trying to calculate in the first place. So it was hard to come up with the proof and formalize it as well because of this recursive nature. So the fix was we modified the expression to be an upper bound rather than an exact term, and we fixed the formalization through that as well. In Theorem 5, one of the sub-cases, which I stated in the theorem statement as well, like for example, when the user converts neutrons to protons in the deep X state, the statement is violated, so the equity does not increase, it actually decreases. So this case clearly violated the theorem, so we modified the proof and we relaxed the theorem statement. So we make another assumption that in the deep X state, the user does not convert neutrons to protons. And this might seem like a cop-out, but the thing is, our goal is to have the known guarantees of stability. So even if in some cases the stable coin is not stable or it violates the what we're trying to prove, it's important to know those cases so that when we implement that protocol in practice, then we can prevent the users from performing certain reactions. So lastly, talking about future work, some of the key takeaways for this talk are formal methods. Although they are time consuming, they help us in designing robust systems. And writing proofs in rock is not different than writing code. This approach provides great value in high stakes projects where there's a lot of money involved or projects are very critical. And we also sort of came up with a framework for verifying stablecoin protocols in general, not just like the Gluon protocol. And for the future work, in Theorem 2, we, for the formal verification of Theorem 2, we made an assumption, but the future work would be to remove this assumption and also prove it. And also make some proof scripts smaller and intuitive by making use of helper limits and new tactics. Because for one of the theorems, like the proofs were very long, so we should focus on making them shorter and simpler to understand. And also, if the protocol is implemented on any blockchain or using any language, it would help if we verify the implementation itself as well. Right now, we just verified the protocol. So yeah, that concludes my talk. If you guys have any questions, let me know. And I would add some useful links for the formalization, and if you want to read more about the theorem prover that we used.